Hey guys, so today we're going to be talking about derivatives of exponential functions. So first I have the two most common exponential functions, or really the only two exponential functions that you'll need to have to take a derivative of. So first off, the derivative of e to the u. We'll assume that u is a function of x since I'm taking the derivative of this in respect to x. So that means u could be something like just x, or it could be x squared, x cubed, rad x, really anything in that exponent that has all x's in it. So when I take the derivative of e to the u, the derivative is e to the u times du dx. In words, I like to say copy. So copy what you see, and then multiply by the derivative of the exponent. For the derivative of a to the u, a is some constant. It could be any number, 1, 2, 3, 5, e, pi, anything like that. So I have a number to a variable. Again, u is a function of x in this case. So the derivative of a to the u is going to be a to the u ln a du dx. And again, I like to think of this in words as copy. So copy what you started with. ln the base. So you ln the base of that expression. And then lastly, multiply by the derivative of the exponent. Let's look at a bunch of examples where I'm applying these two exponential function rules. Number one, y is e to the x squared plus 3x minus 1. Since e is my base, I'm going to use the e to the u rule. So y prime or dy dx, however you want to write it, is e to the u, copy what you see, times the derivative of the exponent. The derivative of the exponent is 2x plus 3. With these e to the u ones, they're very rarely going to simplify. Usually once you copy and do the derivative of the exponent, for the most part, you're good to go. Number two, f of x is e to the negative x. So f prime x is going to be e to the negative x, copy what you see, times the derivative of the exponent is negative 1. I would definitely clean that up and just rewrite it as negative e to the negative x. All set for number two. Number three, I see that my exponent here has a radical, so I'm first going to rewrite y as e to the x to the 1/2. So that now when I take a derivative, I can copy e to the x to the half and then multiply by the derivative of the exponent. So I use a power rule here, 1/2 x to the negative half. I'm going to rewrite this whole thing and just clean it up. I'm going to leave the e to the x to the half as e to the rad x so that it looks a little bit nicer. And then in the denominator here, I'm going to have a 2 from the 1/2. And then this x to the negative half can become rad x also in the denominator. So here is y prime. Number four, since f of x is e to the sine x, I'm applying the e to the u rule. So copy what I see, e to the sine x, times the derivative of the exponent is cosine x. 5, y is e to the x sine x. So since I have e to an exponent, I'm applying the e to the u rule. So e to the u, copy, e to the x sine x, times the derivative of the exponent. The derivative of x times sine x, since I have a times there, it's a product rule. X is the first, sine x is the second. So first derivative of the second, x cosine x, plus the second sine x derivative of the first derivative of x would just be 1. I can either distribute this e to the x sine x inside the parentheses to get rid of the parentheses, but that's not going to help anything cancel or simplify or really look any nicer, so I'm just going to leave this as is. Number 6, g of x equals cosine of e to the x. So this isn't exactly an e to the u rule right off the bat. Right from the beginning, I can see that I have a trig function and I'm taking the trig or the cosine of e to the x. So I'm first going to do a chain rule where cosine is the outside and e to the x is the inside. So in that case, I have g prime, the derivative of cosine, the derivative of that outside piece is negative sine. I leave the inside alone, the e to the x, times the derivative of the inside. So now the derivative of e to the x is e to the x. I can move that e to the x in the front with the negative. So I have negative e to the x sine e to the x. Not completely necessary, just looks a little bit nicer. All set for number 6. Number 7, y is equal to e to the sine squared x plus cosine squared x. Something should be jumping out at you here that's going to make your life very easy. Hopefully we all know that sine squared plus cosine squared is equal to 1. So y is in fact just e. E is a number, so the derivative here is just 0. Tricky, but super easy in the same breath. Kind of weird. Number 8, y is equal to e to the ln x. Again, tricky, but also super easy in the same breath. So when my e and my ln are touching like this, I know that these just cancel. So in this case, y is equal to plain old x. So y prime is equal to 1. There are 2 videos that I've made that have spoken specifically to trig identities and to simplifying log expressions like this without a calculator. I'll leave the links to those in the description so that if either of these questions didn't seem so easy to you, you can take a peek back at those videos and hopefully that will help clear it up a little bit. Number 3, y is equal to 3 ln e to the x. I'm first going to rewrite this by moving the exponent x to the front. That's just a basic log property so that I have 3x ln e. I know that ln of e is equal to 1 and 3x times 1 is just 3x. Again, I have not taken a derivative yet. This is all just rewriting y. So now when I take the derivative of 3x is just 3. Number 10, y is equal to e to the x plus e to the negative x. When I have terms that are split up by addition or subtraction signs, I can take the derivative of each piece individually, right? I don't need a product rule. I don't need a quotient rule. I don't need anything crazy. I'm just doing a derivative of each piece. So first, the derivative of e to the x is e to the x. And yes, I could multiply by the derivative of the exponent, but that's just 1, so I don't need to write that. Plus e to the negative x, copy, times the derivative of the exponent. The derivative of the exponent is negative 1. So I can rewrite y prime as e to the x minus e to the negative x. 11 and 12, I no longer have e as the base of my equation. So for these ones, I'm going to have to use the a to the u rule that we talked about all the way in the beginning of the video. So if y is equal to a to the u, then y prime is a to the u ln a du dx. Copy ln the base derivative of the exponent. So when I apply that rule here, y prime is going to be copy 3 to the x squared times ln the base ln 3 times the derivative of the exponent, the derivative of x squared is 2x. Oftentimes with these a to the u ones, nothing's going to simplify because you have this ln floating around and a base to a variable exponent. It's just messy and kind of just is what it is once you get there. Number 12, same idea. I have a number as a base, variable in the exponent, so I'm applying this a to the u rule. So y prime is going to be a to the u, or copy what you see, ln the base, ln 4, times the derivative of the exponent, the derivative of x squared is 2x. Number 13, y is equal to pi to the tan x. In this case, pi is still a number, so this is still an a to the u rule that I can apply. So y prime is going to be, copy what you see, pi to the tan x, ln the base, ln pi, times the derivative of the exponent, the derivative of tan x is secant squared x. Number 14, I have 4 to the 1 over x. I'm going to rewrite that 1 over x as x to the negative 1 so that when I go to take the derivative of that exponent, I can apply the power rule. So now y prime is going to be copy 4 to the x to the negative 1, ln the base, ln 4, times the derivative of the exponent is negative x to the negative 2. I'm going to rewrite this just to get rid of these negative exponents. We don't like to have those in our final answers. So this is going to be 4 to the 1 over x times ln 4 over x squared. And there is a negative here, so I'm going to stick that out front. You can stick it out front in the numerator or denominator. Doesn't matter where. Either way, good to go on 14. That's it for derivatives of exponential functions. If you have any questions, feel free to leave them in the comments below. Have a great day.